In this video tutorial, we're going to explore a method for modeling and analyzing a pile-supported foundation with a concrete superstructure in Adapt Builder. And we're going to attempt to model piles using column elements with lateral springs at different increments along the depth of the pile, along with the full multi-story structure in Builder. We're going to be using Adapt Builder 2019 for this example, and we're going to run the model in Edge with Floor Pro. We need to use Floor Pro because the actual pile cap will be an elevated floor that allows us to model the piles below that slab or that pile level. So we'll go ahead and select OK. And the first thing I'm going to do is to develop our levels, and we'll just draw a quick sketch of what we want to do here. So we're going to have a concrete superstructure. Let me redraw that here, and we're going to have a pile cap, and we're going to have piles below this cap. And so we were going to add some gravity load and also some lateral load to this structure. And we want to see how the structure behaves for these piles at varying levels of depth. So the piles themselves will be fixed at the base. You can adjust the modulus and the concrete material assigned to the pile by just creating a new concrete material under criteria. And then what we're going to do is also add levels. So this is actually going to be split into 8 unique levels. We're going to say that this pile is actually 40 feet. This cap will be 3 feet, and then the piles themselves will be 40 feet. So we're going to break this into increments of 5 feet. And at each increment, we're going to add a spring, a lateral spring. So you're going to have a KXX and a KYY subgrade value, modulus value for all of these piles. And we're going to then run the model globally with the inclusion of the springs to evaluate the overall behavior of the system. So this is roughly what we want to model. I'm going to have 10 levels above grade. These will be 10 at 10 feet on center. And this, we're going to just model a fairly simple structure above the mat level. So we want to make sure we have 10 levels above. This is going to be our mat level, or cap level we'll call it, and then we're going to have 10 levels below. We're going to have the base of cap, or excuse me, the base of pile, and then we're going to have pile 1, 2, 3, 4, 5 through 8, mat, and then above that, the superstructure. So let's go ahead and begin with that modeling. I'll go to the story manager to start developing our model. We're going to use this as the base of the pile. So we're going to call this base underscore pile. And I'm just going to add a bunch of levels in here. Okay, this will be 5 feet. We're going to just change the height of these. These will all be 5 feet. And I actually want to, I'll rewrite the name of these here in a moment. Okay, so this is going to be, we're going to call this one here mat level. So we'll change this one to 5. And we'll say that this level here is going to be called top of cap. This is our pile cap, or we could also just refer to it as top of mat. And then above that, we're going to say this is going to be level 2, and so on. So I'll change all of these and we'll rearrange this to have all of our levels. So we have all of our levels assigned now. We have levels 2 through 10, top of mat, and then we have the base of the pile, then 5-foot increments for the pile. This could be broken up as many increments as the user needs to model the varying data points along the length of the pile. So we'll go ahead and close that. If I go to multi-story mode and use the front view here, you can see the varying levels for the structure. So the first thing we're going to do is model the mat, or excuse me, we're going to model the footprint of the superstructure. So I'll go to level 2, just navigate down here to level 2, go to single level mode, and we're going to model some structure at this level. I'll just use the grid settings here to model this. Now I could import a Revit file, I could build a model from a CAD file, and also just draw natively. So for this simplified example, we're going to draw this natively. If you're interested in some of those other methods, we do have videos pertaining to drawing file conversion and also Revit import on our YouTube channel. So check that out if you're interested in those methods of creating a model. Now I'll go ahead and just create a slab. So the slab, we're going to say, looks something like this. Okay, and once we have the footprint, we can define the thickness, the material property. We're going to use concrete 1 for the superstructure, and then if we wanted to assign a different concrete for the mat or the piles, we could also do that. And the next thing we'll do is just add a few walls. So I'm going to add a core in this middle portion, and I'll add another core here. We're going to add a couple of openings in that core. Okay, and I'm just using these model components to do this. I'll add a couple more walls. I'll add a wall out here on this edge, maybe another wall here, and then I'll add a few more walls, random locations, and then we want to also add some columns. So these are 10-foot increments. We'll add, let me change the size of the column. Before I add the column, I'll go to column item properties and change this to a 22 by 22 column. And I'll go ahead and add more columns to the model. All right, we've laid out the columns, the walls. The walls, I want to change the thickness. So at the base level, I'll just go ahead and use select by type from the home menu. And if I modify that selection, I'm going to make all of the walls, say 12 inches thick here. Okay, so we have this level. If I go back to multi-story mode and just take this level and copy this level up, I'm going to copy that vertically. So I'll go to vertical, I'll copy this up 9 times, and we've now created that multi-story superstructure. And then I can load this once I'm done modeling the mat. So I'm actually going to load this prior to modeling the mat. I think it'll be easier to select the slabs to load. So in multi-story mode, I'm going to select by type my slabs, and we're going to go to loading, patch load wizard. I'm going to add 20 PSF dead load, and then I'm also going to add for live load. This is unreduced. We'll say it's 50 PSF live load. So we'll just have some basic gravity load on the structure. For lateral loads, I'm going to add EQX and EQY. So just a couple of lateral cases. We'll go to the option for seismic load wizard. First, I'll put in EQX. I'll use the seismic parameters shown here. And we want to make sure that the range is actually from level 10 to top of mat. That's our range for loading. We're going to use a positive X direction load here. This is 0 degrees with 5% eccentricity. We could put in and build as many lateral cases as needed to represent reversal of the load and reversal of the torsion. I'll apply that. I'm now going to change this to EQY. This will be at 90 degrees, and I'll apply that. So we have just a couple, again, basic representative load cases for lateral and gravity for the model. Once that's done, we're going to go now back to, let's go to our default display. I'll go down to the top of mat. So this is our top of mat now. And here we want to develop the foundation slab that we're going to use for modeling really the pile caps and the piles. We're actually going to represent it as a mat with piles. So I'll turn back on my grid, and I'm just going to build some mat slab, and I'll have thickenings for these other for the core walls and some of these perimeter walls. So we'll go ahead and I'll just draw a mat. This is just represented with a 10-foot offset based on the grid settings. Okay, that becomes our mat. We're going to make that mat 20 inches thick, and I'm going to thicken up a few of the portions for the walls. So we'll do a thickening here. This thickening we'll say is going to be 32 inches thick. Had I imported a CAD file into this level, I could then convert that CAD file into a true representation of what the foundation is. So this is just building this on the fly, but there are tools, to make sure this represents the actual foundation that the user really wants to model. And then we'll go ahead and just add thickenings on a few of these other areas. So we're going to change let's change the grid to 5 by 5. Okay, and we're going to nest this slab inside the smaller slab, which is acceptable. We'll do something like this. I'll do this one a little differently. We'll do that. And then this one, I'll just do a boundary like that. So if we wanted to check the geometry, we could use the section cut tool, and I can cut through these thickenings. So you can see we definitely have the thicker slabs obviously underneath these walls based on what I just modeled. Okay, I can then delete those. Those are just cut lines. So we'll do design section, delete. This becomes our mat slab. The next thing we want to do is model piles. So what I want to do in order to model my piles, I'm just going to put the piles at 10-foot spacing. And everything at this level is above, all of these columns and walls are above this mat level. Now I'm really wanting to model piles below the mat. So in order to reference these properly, what I'm going to do is I'm going to use multi-story mode so that I can see my location of my columns and walls. I'm going to go to multi-story mode, and I'm going to set the active plane where I'm modeling to the top of mat. Okay, so that's the plane we're currently on. Now, what happens in this case, and I could also do this in single level mode. So if I'm working in multi-level mode, just what I wanted to mention was the program will model whatever components you add based on the active plane. So since top of mat is active, everything that I add to the model will be below that that level, below that slab. And you can see now that if I go ahead and go back to single level, I'm only seeing the mat slab. I'll turn back on my grid settings. And again, we're going to go to a 10-foot grid. Okay, and I'm going to now disable, or let's say hide, the selection of these columns and walls. So I don't want to see those. I'm just going to right click, hide that selection for a moment, and then I'm going to go ahead and start adding the piles. So if I go to model, column, this is really going to be a pile, and I'm going to go to a circular section here. We'll say that these are going to be 16-inch diameter piles, and I'm just going to add a pile every grid point. This is going to be a lot of piles. In fact, let's space them at 20 inches on, or 20 feet on center, just for sake of the example here and expediency. So we'll do a pile here, kind of in this form. We might have to add a corner pile, for example, there in some spots, but we'll go through this model and begin adding all of our piles in the structure. Okay, we have our piles set. If I go to a side view, we have the piles down from top of mat to pile 35. So what I can do now is add lateral springs. Now I'm actually going to copy these piles downward. You'll see here we have the column and walls missing because I hid them. If I just right click show all, that will show those again. Before I actually copy these down, I'm going to add lateral springs to these piles. So we'll go to a top view again. I'll now go back to single level mode and navigate down to this level here, and I'm going to model springs. So we're going to do a point spring. For the point spring, I'm going to set the K Z value to 0, and then I can set my modulus, subgrade modulus for compression tension for Kx and Ky. So we'll just use some fictitious value here. We'll say let's say 1,000 kips per inch. Actually, let's say 100 kips per inch for both values. This is compression and tension. Once I have that set, I can now model that spring element at the location of the column. So I will just select these columns, place these springs. If I select all of my springs here, like so, I can then copy and replicate. So I'll just select Control Shift C, say I want to copy from here, and just fill these in along this grid. Okay, we're going to delete the ones we don't need, and then I can go back to spring and add those that I need to fill in at the rest of the pile locations. So we have now our springs. I'm going to take that, I'm going to replicate the springs and the piles down 7 times. So I'll go to modify vertically. I'll copy this down 7 times. And now if I come back to multi-level mode, you can see I have the piles. Now you likely would have to change the stiffness values for the springs at each level based on your soil profile, but this just shows how you can model the system. If you need to represent an offset for these upper level piles between 35 and top of mat, I'll go back to my, let's say, level top of mat. I'll just select this and I can offset these. So I'm going to go to modify selection. We're going to select column offset at the top of the column. I'm going to offset this, let's say 24 inches. A positive value is downward. Oops, wrong offset there. Let me go do that again. So this needs to be 0. The Z offset should be 24 inches. And we offset that column. So looking back at our caps with the piles, we have some offset like a socket into the cap. Okay, this is what the structure looks like in this respect. If we needed to assign a different concrete material to the piles, we could go to criteria, concrete. I would add maybe a second material. I'll call this pile. Set the values in this dialog for your properties for that concrete type, including modulus, elasticity, self-weight, shear modulus, etc. And we could then select our piles. And after selecting the piles, we're going to go to modify selection, and we'll use material pile, and that changes the material for that pile. So this is what the structure looks like if we go to the rendering. This is our pile system with the superstructure. I'll go to loading and just add EQX and Y to a couple of the load combinations. So for service, I'm going to clone this. And we'll call this service EQX positive. and then we'll do okay, and we'll change these to no code check. We just want to get a result. We don't want this to design those combinations for anything. For example, we could check deflection, drift, soil, spring reactions, etc., but we don't want it to design any of the elements for these combinations. That's what the no code check is for. So we would say this might be 1, -1, 1, -1, and let's assume we're using 0.9 times the self-weight and dead load, no live load on the structure. Okay, and then for this one, we'll do the same, 0.9 for our gravity loads, our gravity dead load, nothing for live load. And that sets the combinations we want to evaluate. I'll go ahead and save the model. We're now going to just run the analysis. So we'll go and analyze or mesh the structure. So in multi-level mode, we want to mesh the entire structure here. We'll mesh this at 3 feet with a 1 foot node shift. We now have our meshed structure, and we're going to now run this globally for the set of combinations we just added. So we'll go back to execute analysis. We're working in multi-level mode, so by default, this will run the structure globally, and I'll just run it for these few cases that I had set with both gravity and lateral loads. All right, so the solution takes just a few minutes to run with the springs included for that set of combinations, maybe 5 minutes or so for this model. This finishes the analysis of the model. Just a few things that may be of interest once the model is run. I'll go back to my default display just to clear the mesh from view. And we might want to just look at the overall deformation of the structure. So I'll go into my result viewer, and we're going to look at the lateral X deflection, for example. If I go to my 3D view for lateral X, we can see the overall structural behavior for positive EQX with gravity. And you can see there's some interesting behavior going on down at the base of the piles, especially where we have walls and large displacements near these walls. We could do the same for Y direction, for Y loads, etc. So one thing you can do is just check the global deformation just to make sure that it might be within expectation, make sense for the input that you've made into the model. Just for more specific results, we can always go to any specific level. So if I want to go, for example, to the top of the structure, to level 10, and review the results for deformation, we can go here to the slab deformation. This might be, again, for the X direction, and check contours for deformation here. So this is deflecting quite a bit, obviously, 21 inches of deflection at the top level. If I navigate down into the building, we can see additional locations of displacement. So this obviously was not sized for proper spring stiffness interaction with the soil superstructure, and the seismic loading was arbitrary, so we had a fairly high base shear for the loads applied to the structure. If we go down to the lower levels, let me get down into the piles. We may want to see the reactions of the piles. So I'll turn off the deformation. I'll go back to global viewing of the structure. I'm actually going to select everything above, and I'll just hide that. I'll select my slabs and choose to hide that. And now I want to look at my axial reactions in my in my piles. So we'll go now to for any load combination selected here, including the envelope. We could select envelope as well. We're going to go to column and action for combination, look at axial forces in the pile. So this will show and report along the length of the pile just the axial forces in those elements. Yeah, you can see there's some that are taking quite a bit more axial load than others for this example. Those can also be reported tabular wise. If we go to the column report, so we can produce a tabular report for column reactions as well as an XLS report for column loads from FEM and also from a tributary load takedown. We can look at other actions for column, shear, moments, etc. using these actions in the column results table. Let's go ahead and deselect those axial forces. The last thing we'll show here are the reactions for the springs. So under reports again, we're going to go to analysis reactions and point spring reactions. If we select this, the program will produce an RTF report in Word that gives you the spring reactions for those springs that we added at different levels, varying in depth along the length of the pile. And that report would look something like this. Now you can see at certain levels, at certain point springs rather, we have significant reactions shown here. So those might be the point supports at the base of the structure. These are the point support reactions. If we navigate down, we should also be able to pick up, point spring reactions as well. So this includes a mix of both point springs and point supports in the output that we can gain from this option here. So we have point support and then point spring, which is formatted in the same context in terms of an RTF document. And this would be the point spring reaction report for the same structure. I'll go ahead and show the entire structure now. As far as the superstructure goes, the user could use these global results to design elements within the superstructure. So if you wanted to design the shear walls, for example, for the lateral loads, we could use this model with the pile interaction for the shear wall design, or we could say, well, we really just want to assume that the base is fixed, so I might actually just strike out all of the piles, strike out the mat, and assume that this is just a fixed base or pinned base at some of the supports, and then run just everything above this level. That's another way to analyze this. There are other options in the program where if you don't want to model the actual piles, we could just model this mat. So one thing I can do here is say, well, I don't want to model the piles and the springs. I just want to model, let's say, the mat with the springs at the mat level. This becomes more of a mat foundation versus a pile type of a analysis. And what I can now do is just convert this model pretty quick. I'll go ahead and turn on the point springs. I'm just going to delete all of this. And I'll save this as a different file. Okay, we have a mat at top of mat level. Everything below this is ignored at this point. So at this level, I still need to support a structure somehow. So I could, again, go back in and put in, rather than model the piles, I could just put in point springs. Here I'm just going to model this as a compression spring. So now this just becomes a mat structure, and we'll go ahead and just add a spring. And this spring, again, has some characteristics to it. We're going to call this a compression-only spring with a vertical and a lateral non-zero value for my subgrade modulus inputs. Once that's done, now that the structure really rests on area spring, when I analyze the structure, it's a compression-only spring. So the program senses that, or it picks that up, and it allows us to substitute the spring with fixed supports or run the analysis directly with compression springs. If I substitute this and run the analysis, so once that's done, we've obtained reactions at the base of the structure, but if we look at the deformed shape again, because we use substitution, if I just look at the vertical deflection, we're going to have no displacement at the mat. The mat is essentially ignored when we run the model with substitution. However, we can now apply the springs or the mat with springs and use the reactions obtained from this first solution directly on the mat. So if we go back, and I'll go down to the mat level, and at this level I'm going to rerun in single level mode. So we can execute the analysis, and here we're just showing some of the flexibility of the integrated approach used within Builder. We started out with a pile supported superstructure. Now we've actually transitioned into a mat with an area spring in the same instance of model use. So we'll just rerun this in single level. This will inherently capture the participation of the springs because the springs are modeled in the single level, and I'm going to include the reactions for lateral and also gravity from the FEM global solution that I just ran. And now I'll just rerun this level with those reactions, and then I could evaluate soil pressures and different results required to check serviceability and strength requirements of the mat. We could generate reinforcement by use of strips and so on. We'll save that, and if we go over to slab, let's say stresses, and look at the soil pressure, you'll notice that this does not allow me to check soil pressure in this instance because we're in Floor Pro. If we transition into mat, we can check the soil pressure here. So I'll just save the model, close out of this. I'm going to reopen the program, and I'll transfer this over to mat, and I can recall the same model and solution. I'll go ahead and open up that file. Okay, we'll navigate back to the top of mat here. I'll reopen the result browser, and from slab soil pressure under the stress maps, we can look at the soil pressure now for this slab. And this is with the applied reactions on the mat from the global analysis in this second method that we've run. Additionally, we could also break the slab up into design strips and design certain portions of the slab. So if I want to design this area right here for this mat, I could set up my design strips. I might have a strip along this line, maybe here, and maybe one along the middle there. And in this direction, if I just add a boundary there and there, I'm just isolating the slab into this location. Let me stretch that boundary up. Okay, I have my strips here, and now if I design those sections, these sections have to be designed in Floor Pro mode because this is technically an elevated slab in the program. So we would have to be in Floor Pro mode to design the. Okay, back in Floor Pro mode, I'll go back to Floor Design, design the sections, and within those strips, we can now obtain just different actions along the cut path. So we'll go to actions, for example, bending, shears, etc. And based on these cuts, the program will add reinforcement for the different combinations that we've evaluated. If I select to generate rebar, this is no rebar is required or selected for this combo because the combo that we actually ran the model for was set to no code check. So, but this would allow us to get at least the actions for this particular instance along the cut paths for this thickened footing. If you have any questions about any of the capabilities of the software, please contact us at support or sales@adaptsoft.com. We'd be happy to answer any questions. Thank you.